Hello and welcome, and thank you for joining us for this webinar on the LGR post-analysis software for analysis of liquid water isotope analyzer data. Very glad that you could join us today. You will see here the new version of our post-analysis software, and I'm going to just run you through using this software to analyze the data off of a LGR, liquid water isotope analyzer instrument. This software does analyze data from old and new versions of the instrument and all versions of the instrument, both with the 17 measurement and without. We'll start off by showing you this handy little help menu here, which will get you directly to the user manual of this software. So if you have any questions, this is always the first place to start. So let's jump right in, analyzing some data. So in the File menu, we'll start by loading up a data file. Depending on the type of analyzer that you have, you will see that you have either a data file that starts H2O, this is from our older version analyzer, or you will have a data file that starts either T-LWIA or LWIA. For these analyzers, the T-LWIA or LWIA analyzers, you want to use the file that has the F here at the beginning of the number. For the analyzers with H2O, you want to use a file with the TXT extension. So those are the files from the analyzer that are used by the post-analysis software. So we'll load up this file right here. And as you can see, it starts off and does a little bit of processing right off the bat. So here at the top of the page, you see the data file path. This is the file of the data file the file path for the data file you have just loaded, and the current data file name that you're analyzing can be found here. When the software opens the file, it attempts to automatically detect the number of injections per measurement. That number starts up here in the upper right corner. You should always check this number to make sure that it has determined this correctly. In particular, if you measure the same sample more than once right at the beginning of the file, the software can get confused and get this number incorrect. You can always change it either by using the up-down arrows or by typing directly into the box. Here in this injection data box, you see all of the raw data from the analyzer, including injection number, name, water, injected amount, and then the raw data for the isotope ratios. If your analyzer does not measure 17, you will find that all of the 17 values throughout the software will just be blank, but the software still works perfectly correctly. You will see here also this column, this remove column, will show you injections that have been removed for one reason or another from the data analysis. So we're going to talk a lot about removing injections, but I just want to mention here that you can always manually include an injection by double-clicking a previously removed injection, and that will include the injection in the analysis, or you can manually exclude an injection if you know, for example, that something went wrong. And also in this injection data, you will see a 4-letter flag which gives you information about that injection. Some of the flags are set by the software. These IGNR or ignore flags are injections that have been ignored for sample-to-sample memory. You will see if you manually include a sample, it gets the include, and if you manually exclude, it gets the user. We'll come back and look at this injection data more as we move through the tutorial. Over here is the list of unique samples. It's exactly that. It is a list that the software comes up with, which is every unique sample name in the data file. Those sample names which match samples in the standard library are automatically marked as standards, and their known isotope values are read out of the standard library. This software ships with a default standard library which has all the LGR and USGS and several IAEA standards automatically included. We'll talk a little later about making your own standard library for your standards. You will see other samples are down here that were not in the standard library. If one of those is in actuality a standard, you can always double click and then single click inside the boxes to manually add the standard values. All right, So this is the data as it is loaded, and the next thing that we'll do is go to the post-processing file menu and run the post-processor. So once the post-processor has run, you can see we have a lot of data here down at the bottom. So looking down here at the samples, this is where the data for your samples comes out, and this gives you just an overview of how the sample measurements went. So you can see here the accepted number of sample measurements. Those are sample measurements that were utilized and measured. If you have a lot of things, injections that are filtered out, you will have fewer accepted sample measurements, but you can see in this case we have a very large number. You can see the name of each sample measurement and its processed values here. So here, this first 473 corresponds with the first measurement of 473 here in the injection data list, and you'll see now that the processed values, so this is after standardization, show up here. So these numbers will match these numbers over here. These precision metrics are a weighted average of the standard deviation. So this deuterium number is a weighted average of the numbers in this column here. And so this is a way of keeping track of the precision of the analyzer over an entire data set. So moving on from the samples, we'll take a look at the standards box here. This gives you information about the standards that you utilized to do the calibration, to do the standardization. So here you see the standardization method. At the moment we're using the block standardization. We will talk in detail in a few moments about the different standardization methods that are available. The accepted standard measurements is the same idea as the accepted sample measurements, and the accuracy metrics give you information about the accuracy of the run. So these metrics are the average deviation of the standards from their known values after the calibration has been implemented on those standards. So these values are only active if you have 3 or more standards, because of course 2 standards always perfectly fit to a line. You might have noticed as I ran over these that the cursor changes from an arrow to this double-headed circular arrow, and that gives you the information that there is a hyperlink on this data value to a corresponding different screen. So if I click on that, that takes us directly to the processed standards screen. And this gives us more information about the standards that we have used to do the calibration. And I chose this data file on purpose to let you see one important thing to note from the process standards screen. You will see here that these standards, especially in the deuterium, have a very distinct pattern where one standard is low and then the next 2 are slightly high, and then one is low and the next 2 are slightly high. This type of pattern indicates that there may be a slight issue with these standards. Either the ampules have been open too long so that one or more of them is fractionated, or perhaps there's been a slight amount of contamination. And this isn't a very large pattern. You see here that these deviations, the average deviations, are still only about 0.3 per mil. But whenever you see a pattern like this, you want to take a look at the standards. And for this reason, LGR very highly recommends always looking at this process standards pane to get an idea of how well the standards are behaving. Because of course, if the standard measurements are poor and you use those to calibrate your sample measurements, the poor quality will translate into your sample measurements. On this pane, you see some of the same information that we saw on the summary pane. So these are those same average deviation numbers, the same numbers of accepted standard measurements. Of course, we have a lot of new information. Here is that deviation from known plotted versus injection number. So you can see for each isotope and for each injection what the deviation is. And on this side, this fit to standards is showing you the actual calibration curve that has been corrected. So this best fit line to the 3 standard measurements, in this case USGS 46, 47, and 48. And you can see that by changing these radio buttons, you can see that for each of the various isotopes. Now, one nice feature here, if you come back over to this graph, you can click on this blue line that you see here on the left, and if I hold down the mouse button and translate this blue line, you can see it will move over the data. Notice as I move this that the injection data block, which is in the top right of the screen, is moving as well to show which injection we are hovered over on the blue line, and the fit to standards graph on the right is moving as well, although it's much harder to see, but you can see that the slope and intercept numbers are moving. And that is also showing us exactly the best fit line, which is associated with the data that the blue line is over. So in many of the graphs, you will see that by moving the cursor line on the graph, you will see the injection data table move. This way you can take a look at any particular data set and see if there's a particular problem or if the best fit line doesn't look so much like a line. So now I'm going to move back to the Summary tab. Two ways to do that. You can either go to the View menu and click Summary, or do Control-A is the keyboard shortcut. Back to the Summary tab. We've talked about the standards and the samples. Now we're going to talk a little bit about the filters. So the idea is that the software automatically filters the data to reject any poor injections, and then you can move ahead with the analysis. So in this case, you will see that the number of accepted injections is 806 out of 816 utilized injections. So that's an excellent acceptance rate with a rejection of only 1.2%. You also see here the number of flags that were made by the analyzer. So these are flags on the analyzer. Frequently you'll see the press or DENS flags on the analyzer. Those show up here to give you an idea from the analyzer's perspective about how the run went. And then here you see the most active filters. So these are the filters that have flagged or rejected the most of the injections. So we'll talk at great detail about the filters in just a moment. The internal control box down here keeps track of a laboratory internal control. And this is a way of keeping track of how the analyzer is performing that LGR highly recommends. So the recommendation is to have a water of known isotope ratio that you created in your laboratory that you run in every analysis. And the basic idea behind this is that you run this sample as an unknown, but really you know the value. So you can check to make sure that every time you run the internal control, it gives a value close to that which you're expecting. And that way, if you know that you can accurately measure the value of your internal control, it gives you a high degree of certainty that you can also accurately measure the value of your unknowns. So in this case, the name of the internal control is simply IC. You notice again that my cursor has changed to that little arrow indicating that there is a hyperlink here. And if I click on that hyperlink, it will take me directly to the internal control configuration where I can put in the name that I'm going to use for the internal control. I can put in the known isotopic composition, and I can enter the deviation bounds. So these are how close you want the measured value to be to the known isotopic composition. So that will depend on your application and the precision that you need for what you're doing. So that's the summary page, and as I said, under the View menu, you can get to the summary page. You can get directly to that process standard page that I do recommend looking at every time you do the analysis, and you can also look at the data set plots page. So this pane gives you a wide variety of plots so that you can look more closely into your data. And so the first one that comes up is the raw ratios, and that is literally the raw data that has been loaded from the data file out of the analyzer. So looking at this, you can see that the points are color-coded. So here you see gray points are the points that are ignored. We do recommend running, depending on the isotope ratios of your samples and standards, running a number of injections per measurement. We'll ignore the first several measurements in order to account for sample-to-sample memory, and then utilize usually the last 4 measurements to average together to be a complete measurement of a sample. So some number of injections, the first few injections are ignored, the last 4 injections average together to create a measurement. In this case, I'm doing a relatively large range on these USGS standards, all the way from -236 all the way up to almost 0 in deuterium. So I'm using a relatively large number of injections per measurement of 10, and I'm ignoring 6 of those and keeping the last 4. For a more narrow range, if you were running from maybe 150 up to 0, you could use 6 injections and ignore 2. So those ignored injections are gray. Standard injections show up cyan. Sample injections show up black. Warnings on some injections will show up orange, as you see here, and excluded injections, rejected or excluded injections will show up red. And that's the case, that's the color scheme that's used for all of these graphs. So this is the raw ratios. You see every injection in this graph. The processed ratios is after the standardization has been completed, and rather than this showing the injections, this actually shows the measurements. So you'll see one measurement for each sample or standard. Again, standards in cyan, samples in black. The process deltas is the same, just showing in delta as opposed to in ratios. But on this graph, we have the additional information looking at the internal control. So here you see there's 8 measurements of the internal control in 4 groups of 2. And you can see that the bounds lines have been added. That's a little hard to see here, so let's take this opportunity to talk about the tools that we have for manipulating the graphs. You've already seen the first tool. That's the tool that allows you to pick up the blue line and move it side to side. Notice that on these graphs it's also the case that it also, as you move the blue line, you also scroll the injection data block. The second set of tools includes the zoom tools. So this is a box zoom, a horizontal zoom, a vertical zoom, and this is a zoom out to show the entire graph. And then this is a click zoom, a click to zoom in, and a click to zoom out. So in this case, I'm going to use here the vertical zoom so that we can zoom in on the internal control. So the internal control within bounds, it will show you green circles around black. Out of bounds will show you orange circles. And you can see here the bounds that I have set are these dotted lines. So we're going to continue with the analysis here, but after the analysis is complete, if you do see internal controls which are out of bounds, that would give you the indication that you need to take a look at the data immediately preceding or following those out of bounds internal controls, because again, as I stated before, if you can't measure the internal controls to the accuracy that you are aiming for, it gives you some pause as to whether the samples around that are measured to that accuracy. We will improve these internal controls by changing some of the settings for the analysis in a few minutes. This last tool here is the pan tool. So if you have this hand, if you click and hold and move, you can pan around the graph to see different things. And it's most useful when you're zoomed in like this. All right, so the next graph is the processed versus measured. So this shows exactly what it says, the measured ratios on the x-axis, the processed ratios on the y-axis. You want these to show up as a line, of course, because that's what you expect to see is as much as possible, one-to-one line. If you do see some standards, especially that are off the line, that'll indicate either that there's possibly a wrong value for the standards, or perhaps that 2 standards have gotten switched. So it's nice to take a look at this. This one is in ratios. We have the same graph also in delta. You can see that. The next graph shows the measured values divided by the standard deviation. So this gives you an indication of the signal to noise inside the instrument on an individual injection. And you can take a look in the manual there for some values that we expect the averages to be above those values. If you are finding that your values are consistently lower than that shown in the manual, we encourage you to contact service@lgrinc.com to take a look at those. The ratio adjustments shows how much the measured values were adjusted by the standardization. And so you can see here these adjustments. And in this case, you can see that the adjustments happen in groups. So here you can see there's one group of standards, 1, 2, 3 standards, and the samples that have gone with it, and that adjustment has happened in a group. And this will be important in a moment when we start to talk about different standardization methods. So you can look at adjustments in ratio space. You can also look at adjustments in delta space. Again, essentially the same information. This next group of graphs shows us the workings of the various filters. And the first one is the absolute injected volume number density. So in this case, we set the bounds of injected volume outside of which we won't use those injections. So in the standard default values are between 2.5 and 4.5 times 10 to the 16th. I will note here that all of the filters happen in sequence. There's a hierarchy of filtration. So any injection which has been excluded by, for example, this AVOL filter will not be utilized in the next set of filters. And every filter has a 4-letter code that goes with it, so that here in the flag or also in the detailed output file, you can see what filter was applied to a particular injection. If no filter is applied, then you get this norm code. Here we can see that this absolute injected volume filter has no rejection, 0 out of 816. You might wonder why the denominator here is 816 when I'm showing 1380 injections, and that's because the ignore filter, which isn't exactly a filter, but the ignore is the first filter, if you will, and so those injections are not included in any of the filters subsequent to that. After the absolute injected volume comes the volume running average filter. So this filter calculates a running average of the injected volume over a length which is fully settable, and then a bounds in a percentage of that, bounds above or below. So here you can see anything in the red area, either above the upper limit or below the lower limit, will be excluded by this filter. So here you see that there are several injections, these red ones here, which are being excluded by this fluctuation of the volume filter. The reason that this filter is useful in analyzing the data is that slow changes to the injected volume, such as you see here, a slight decrease and a relatively slowly, do not tend to affect the data nearly as much as abrupt changes like you can see here or especially here. And so these abrupt large changes, those injections it helps to exclude. So now you see that FVOL has rejected 5 out of the 816 rejections. The next filter is the standard deviation of the injected volume. This filter helps to detect incomplete evaporations from the analyzer. So you've injected the water and the analyzer has waited a certain amount of time, and then unfortunately the measurement started a bit before the evaporation was complete. So of course that can create problems with fractionation, and you don't want to utilize those injections. So in this case you can see that there are a few places where there's been incomplete evaporation. I would note the instrument also checks for incomplete evaporation. It does that with the DENS flag, but the instrument will detect really egregious cases of incomplete evaporation, where this SVOL filter is able to detect much more subtle cases. If you do have a DENS flag from your instrument, you will see a large spike in the SVOL, but this filter is able to detect some of these smaller ones. I would also point out here, if we zoom in on this data, it's helpful to notice you see the red points are injections that have been excluded by this filter. But if we zoom in over here, you can see some black points that are outlined in red. Those have been excluded by a previous filter. So you can always tell the difference on excluded injections. And down here you'll see 5 out of now 811 injections have been excluded by SVOL. This is now 811 because the 5 out of the 816 that were excluded by the FVOL filter are no longer counted. The next filter is the temperature variation filter. The vast majority of you now have temperature stabilized enhanced performance instruments, so you will always see a graph that looks exactly like this, where there really is no temperature variation at all. If you do have one of the older instruments, you will see a graph with a lot more motion and movement to it. So I definitely recommend taking a look at the TVAR section of the manual if you do have an older, not temperature stabilized instrument. This ratio outliers filter is a statistical filter. All of the filters that I've told you about so far are physical filters. They work on some physical property of the injection that we can take a look at, usually either the number density of the injected water or the temperature. This filter is a simple statistical filter. So if you take a look at one particular group of injections, these first 6 have been ignored due to sample-to-sample memory. You can see from this set how important that is to ignore these first few injections. The last 4 have been averaged. So this filter takes the average and the standard deviation of those last 4 and checks to see if any of those injections are more than, in the default case, is 3 standard deviations away from the mean. What we have found is if you have the physical filters turned on, you almost never see the statistical filter showing any rejections at all, because the physical filters have handled that in a known physical way. Now we are going to talk about the spectral contamination identifier. So this is a really important filter that the post-analysis software incorporates. For those of you who have the older instruments that start H2O, the spectral contaminant identifier will not work for you in this software. You will need to continue to use the standalone SCI software. And the reason for this is that when LGR upgraded our instrumentation, we took that standalone SCI software and we did half of that work on the instrument itself and the other half of that analysis here on the post-analysis software. So if you have the older instrument, like I said, you'll have to continue to use the older SCI standalone software, but with newer instruments, the SCI information will be right here in your post-analysis software. So the SCI, is a spectral contaminant identifier, does just that. It identifies contamination in the water, generally from alcohols, that creates a change in the measured isotope ratio. In this case, you can see that one of these samples does indeed have narrowband spectral contamination. So that indicates that you're very likely to have some methanol contamination in this water sample. There are a couple of things to do about this. One thing is to measure it on a different type of instrument, such as an IRMS, and the other way to handle this problem is to use a correction such as that is done in the Schultz paper, and the reference for that paper can be found in the manual if you want to take a look at it. I would note here that even though not all of the injections on this measurement have been flagged, it's clear that it's all of the measurements of this particular sample do show a bit of contamination. The narrowband contamination, which is the one you're looking at here, tends to take a look at contamination by things like methanol, and then the broadband contamination would show any contamination by ethanol and higher alcohols. So in this case, we have no broadband contamination. The next graph, a set of graphs that you see, is not really a filter, but a look at the precision on the data. So here you can see the standard deviation of each measurement plotted against the injection number. So these are individual measurements. These are not injections. And you can take a look at the standard deviation of the values. You can change on all of these graphs, or most of them, you can change the display to look at the various isotopes. So this is the deuterium, oxygen 18, and oxygen 17 isotope. The values of the standard deviation cutoff, the upper limit up here, have been set to match the precision specifications of our newest analyzers. If you have an older analyzer, you may find that you need to change these values to match the precision that you are expecting to get from your analyzer, and more information on that can also be found in the manual. The last two graphs available on the dataset plots are standardization graphs. So this first one appears when you're doing the block standardization. And the block standardization is a very common method of doing a standardization. So if we take a look at any one block, it's not important which one, you have 3 measurements of standards, and those are interleaved with measurements of samples. So the way this standardization works is it takes this particular group, it takes this measurement of USGS 46, this measurement of 47, and that measurement of 48, creates a calibration line, takes the slope and intercept from that line, and uses that slope and intercept to adjust the values for these 3 standards and all of the samples interleaved. So one calibration curve for this entire block of samples and standards. So in this case, you see that we will have 17 standardization lines, so 17 slopes and intercepts, 1 for each block. And again, you can always take a look at those slopes and intercepts by looking at the process standard. So as you move through, you will move through this blue line, you'll see 17 different slopes and intercepts, 1 for each block of standards. Now, I would point out to you that we have more information than just the particular information in one group of standards. You will note by looking at the raw ratios that you can actually see that we have temporal information on how these standards are changing over time. You do see a little bit of drift in these standard measurements, and we do have that information because we have measured these standards over time. So by just utilizing a single block of standards, we're not utilizing this time-dependent information that we have collected. So one of the major changes that we've made and upgrades to this software are ways to utilize that information, that time-dependent information of the standards. So I'm going to show you that if we change this to a different standardization method, I'm going to use the linear spline for a moment. If we change to a different standardization method, then run the post-processor again to implement that method. Now, rather than the standardization blocks, you will see we have the standard fitting graph. And if we look at that graph, you can see what we have done. I'm going to zoom in here on the USGS 47. What we've now done is we've fit a line in between each measurement of the standards. So this lets us utilize the information that we have on how the standards are changing. So for each standard, I've zoomed in on 47 here, but for each standard we have fit a line through the data. Now if we want to standardize a point, say this point here, this sample, so say sample number 7, we want to, no, it's not updating for me, there we go. Say we want to utilize this sample right here. Rather than using this value of 46, this value of 47, and that value of 48, as we normally would with a block standardization, now we can use the interpolated value, this value here of 46, that one of 47, and this one of 48. So this allows us to create a local calibration curve for each sample and allows us to utilize the temporal information. So we've included in the software this linear spline, which draws a line through each of the values. We've also included a cubic spline, which fits a smoother curve through the values. So if I run this, I can show you what that looks like. So now you see, if we zoom in, we fit a curve through the line. Now, I tend to find that this cubic spline does produce the best values for the data on an overall basis, but if you want to find out for an individual group of samples and standards for an individual run, what gives the best values. We also have an automatic selection, which will automatically run through the various options for the standard fitting. I seem to have mistakenly not told you about the smoothing spline. The smoothing spline is the same as the cubic spline, but it does not force the spline to go through all of the points. And this fitting method tends to be the best when you have an outlier in your standards, although with all of the various filters turned on, that doesn't happen as frequently. So we usually find the smoothing spline not to be the most useful, but we do still have it as an option in case it's needed. So as I was trying to tell you, you can turn on the automatic selection mode. And what the automatic selection mode will do is it will run through all of the various methods for doing the fitting, and it will compare the accuracy metrics on the various methods, and it will choose a method that it feels like gives the best accuracy. So if we run that, you can see it's processing and then processing again and again. It's running through the processing, and it's going to choose the method that gives the best accuracy metrics, the best average deviation from the known. I will, however, point out that that gives you perhaps the most accurate standards, but it doesn't always give you the most accurate data for everything. So I'll note over here in our internal control, with the block standardization, you see that we have 3 out of the 8 measurements within the bounds that I set. And if instead I change from the block standardization to the cubic spline standardization, keeping an eye on this internal control number, you can see that that improves to 6 out of 8 measurements. So I would recommend that you always use an internal control and that you use your internal control measurements to determine which standardization method is best, rather than the accuracy metrics. We couldn't incorporate that into the software because not everyone uses the internal control function, but we do recommend that everyone does use it. So now I'd like to walk you through how to change the settings and how to set up the software to run the way that you most like to use it. So under Options, Advanced Settings, you can see here, this shows all the filters that are available, and they're all fully user configurable. It starts by rejecting any injections that have been rejected by the software on the instrument itself. So if the instrument has flagged an injection as being a poor injection, we highly recommend not utilizing that particular injection for data analysis. Similarly, injections that are flagged on the analyzer as being DENS or sometimes press are usually very significant incomplete evaporations, and those are sometimes so significant that the fractionation carries over into this next injection. So we recommend rejecting any injection which follows a press or a DENS injection on the instrument, and those are labeled with the 4-letter code after. The LWIA flagged injections are labeled with the same 4-letter code that comes off the instrument, so you'll continue to see a DENS flag over in the flag column. The next filter is that ignore filter that we've talked about, to ignore leading injections. In this case, I've set the leading injections to ignore to 6, but you will change this number to match the number of injections that you've used on the instrument, and change that as you change ranges. You can enable or disable the feature here, and this is a new feature to detect repeats. So I'll show you what that means and why we've added that. So if we look again at the raw data, and we look here, let's look at some data here. So here we've done 10 injections of a standard. We've ignored the first 6 due to memory. We've averaged the next 4. Here we've done 10 injections of a sample, ignored the first 6 due to memory, average the next 4. Now we have done an additional 10 injections of the exact same sample. Of course, there's no sample-to-sample memory happening here because it's the same exact sample. So there's no good reason to ignore these 6 injections. They're all perfectly good injections. So what that detect repeat does is it detects when you are repeatedly measuring the same sample over and over again, and it allows those injections which would normally be ignored to be utilized instead. So by utilizing more injections, you can hopefully improve the precision of the averages. Here on the summary screen, you can see this N column shows how many injections were utilized for that measurement. So this first injection of 473 was coming off of a standard, so we've used 10, ignore 6, 4 injections. The next measurement of 473 came directly after this measurement, so all 10 injections are completed. So you'll see that that is included here. That pattern is repeated here. Here you see only 3, and what that indicates is that some of those injections were excluded due to a filter. So here's that first measurement of 473 there, 4 injections. This is the second measurement, all 10 injections, and then third and fourth, and then if we come down, we'll see right here that this measurement of 473 has only 3 injections because 1 was excluded by the SVOL, and then the next measurement has 8 injections because 2 of them were excluded by SVOL. So that's what this column will show you over here. Looking back again at our filtration in our advanced settings, these are the settings for that absolute injected volume filter. You can change the upper and lower limits and enable or disable the filter. Same thing for the injection volume fluctuation filter. You set the number of points in the running average and the rejection bounds. Again, you can enable or disable that filter. We recommend that this number of points in the running average be the number of points which would be in a standard block if you were using this block standardization. So that's the number of injections between one measurement of standard A to the next measurement of standard A. The injected volume standard deviation filter is here with the rejection bounds in number of standard deviations, and you can enable or disable that filter. The temperature variation filter here, we definitely recommend keeping this temperature range upper limit to 1 degree C, and if you have an instrument which is not temperature stabilized, please do look at that in the manual. These outliers filters, these are those statistical filters I was telling you about. Again, we set those defaults to 3 standard deviations, and you can enable or disable the filters here. For the spectral contamination, because this is such a serious issue in the laser-based measurements of isotopes, this particular filter you cannot disable. You can change it from a rejection of the data to a warning on the data, but you can't turn the warning off because we really want folks to be paying attention to whether there may be spectral contamination. And these values for the limits, these are standard deviations as well. We don't recommend changing those. We've done a lot of work to figure out the optimum level for those filters. The measurement precision here is that last graph that I showed you with the delta values. So these are the standard deviation limits. Again, these are set to match the guaranteed precision of our new analyzers. You can change these from a warning to a rejection or turn them off completely with these checkboxes here. Anytime you make changes to this and decide you might want to go back to the factory defaults, you can use this button here to restore defaults. And for all of the settings in advanced settings, you can load and save the settings file. So you can set this up exactly the way you want it, save the settings file, and then load it later. So I'll show you that in just a moment. The file output is exactly what it sounds like. This lets you configure the output files the way you like them. This post-analysis software always produces 2 output files. It produces a detailed data file, which contains all the information you might need to reprocess the data the exact same way. So it starts with a header in that detailed file, which contains every setting for all of the filters, for all of the standards, everything that you used to process the file. So this allows you, if you want to go back 6 months later and say, I want to process data B exactly the same way I'd process data A, this allows you to take a look at that. It also outputs all the data from every individual injection with those injections flags, so you can see if one injection was, say, manually included or excluded. Since this data file is used more rarely by most of our customers, we recommend keeping all of the data columns output in that file so that you have all the information you might need. The process data file is the file that most customers use. It outputs the process data by measurement, so not all the injections are shown, just the measurements, and you can configure which values you want output into the process data file. I will point out that you have the choice to output the narrowband metric, so this is the metric from this SCI, from the spectral contamination, for both the narrowband and broadband metric for further analysis later. This software has also been updated to include a LIMS compatible output file. So if you are using the USGS Laboratory Information Management System to manage isotope results from your laboratory, you can enable this output, and it will create an additional file which is LIMS readable. The User Settings tab shows additional settings that you may want to use for your instrument. This user standard library path is the path to a standard library that you can create with your in-house standards, and there are detailed instructions in the manual for creating that user standard library. I will just point out here that the software will read both the default and the user standard library, so you just need to put your own in-house standards into that user standard library. The standardization method here we've already discussed what that means, and again, same thing for the internal control configuration. The timestamp format is set here. This timestamp format of the post-analysis software needs to match the timestamp format that you have set on your analyzer. So whatever the analyzer is set to, please set the post-analysis software to that same timestamp format. The post-analysis software is designed to work with any timestamp format that the analyzers can put out. So you can set the analyzer to however you would like it, and then just make sure that this software matches. This box here turns on our sample averaging mode, so this lets the software automatically do the averaging for you if you have measured the same sample multiple times. In this particular case, I've measured each of our samples 20 times, so if I change the replicate averaging mode to 20 and rerun the post-processor, you will see here that it has now changed this to say samples replicate averaging results, and now instead of 20 lines for each of my samples, I now see just the one, and it shows me the average value. And you will notice here that the N value is now very large because that's the number of injections for the entire 20 measurements of this sample. I will also note for you that these averages are done over the 136 injections rather than done over the 20 measurements. And you'll remember that some of the measurements included more injections than others. So you won't get exactly the same results averaging the 20 measurements as shows up here in the replicate averaging results unless you weight that average by the number of injections that are included in each of the measurements. Also on the replicate averaging, if you average a minimum of 10 measurements per sample, you can also have the software automatically output 17 excess. Now, the 17 excess needs to be measured in a highly precise fashion to be of any utility for scientific research, so that is why you need to do such a large number of replicate averages in order to turn on the 17 excess measurements. So here you see that when you turn it on, an additional column pops up outputting the 17 excess that you would expect. The last thing that I want to discuss here is the injected volume correction. And the injected volume correction is another one of the new features of this software, which is really very helpful in getting the most precise data. What we find in all spectroscopic techniques, in fact, is that there is a small dependence on the amount of water that you're measuring to the isotope ratio that is measured. And this is in an IRMS, this is called the linearity correction, so you may be familiar with that term. If you're not familiar with it, this is a way simply of correcting for variations in the injected volume and using those variations to correct the measured values of the isotopes. It's very important that you note that these injected volume corrections are instrument dependent, so you will need to measure these values for your instrument itself, and the user manual for the software goes through how to do those measurements. In this case, I have measured them for the instrument that I used to collect this data, so I'm going to load a user settings file. You can see I've saved my settings as full settings.adv.stg. That's a file that is saved by this software. So I entered it manually and then saved the file. Now I'm going to load it back up. These are the coefficients that I have for my injected volume, and I've turned the correction on. So now, if we take a look over here and I run the post-processor again, you can see I get slightly better precisions, and now that I have utilized the injected volume correction as well as the cubic spline calibration, my number of internal control measurements within bounds has now gone up to 7 out of 8. So if I use my hyperlink here to take another look, you'll see in deuterium, all of my measurements are within bounds. Same thing in oxygen 18. It's the oxygen 17 where I have one measurement slightly out of bounds on my internal control. I'm going to zoom in and take a look at that. And I'm going to see that it's just very slightly out of my bounds. And since it's only 1 out of the 7, I'm going to decide that I can go ahead and accept all of this data, that the internal control is sufficiently close to the bounds, that this is good data. But you can see from looking at the internal control, the block standardization and no injected volume correction, we had 3 of 8 in bounds. By the time we add the sophisticated calibration method, standardization, injected volume correction, you can see that that really brought our internal controls in to where we want those to be. So all of these settings, all the settings on the user settings, the file output, and the data filtering can be saved into an advanced settings file. It is also the case that the software remembers the settings that you have last used, and when opening the software the next time, it will continue with those settings. So a couple of important points to note: if you've had to change settings for a particular data run, you might want to load up your standard settings at the beginning of the next day so that you're not inadvertently using the settings saved from the previous day. An important time when that might happen is on the spline fitting of the standards. So I mentioned that I recommend using the spline fitting at all times, except, of course, if you're going to try and draw a line between each 2 measurements of the standard that you've made, you need at least 2 measurements of each standard in order to fit that line. If you have data that has, for example, only 1 measurement of each standard, you're going to have to use the block standardization. And in fact, the software will automatically detect if you don't have enough measurements of the standards and ask you to change to a standardization fitting method, a spline or a standardization, block standardization that is appropriate for the number of standards that you've measured. But this setting will persist then in your analysis the next time you open the software. So for a linear spline, you need at least 2 measurements of each and every standard. For a cubic or smoothing spline, you need at least 3 measurements of each and every standard. So I recommend each time you load up the post-analysis software, loading up, coming into this advanced settings and loading up your basic settings that you're going to use so that you know you're starting from a clean slate each time. As far as the injected volume correction, these numbers will hold for a particular instrument. So if you have only one instrument in your laboratory, you do not need to change these measurements, although LGR does recommend remeasuring the injected volume correction approximately quarterly because the numbers do change very slightly over time. If you have multiple LGR instruments in your laboratory, do be particularly careful to be using the injected volume correction for the correct instrument because they vary significantly from instrument to instrument, and you can get some very strange results by using the wrong injected volume correction. The last thing that I have to show you is under the File menu, you can save your processed data. And as you save the data, it automatically defaults to a file name. When you hit OK, it will reprocess the data to make sure any changes that you have made, and it will save that data to that file name with one of the files will say detailed, one of the files will say processed. If you've turned on limbs, one of the files will say limbs, and if you've turned on replicate averaging, you will have an additional file which is called the replicate file, and that will be in the file name, which holds just the replicate averaged data. And with that, I think that I have given you a full tutorial of how to analyze data using the new and improved LWIA post-analysis software from LGR. And I would encourage, if you have any questions, to take a look at the manual. And if that doesn't answer your questions, please contact us at service@lgrinc.com. I thank you very much for joining us today and hope you have a fantastic rest of your day.